Okay, last time we were talking about bonding and types of bonding, and we talked about ionic bonding, which is always between a metal and a non-metal. And here, because of their differences in their periodic sort of trends, we will get a transfer of electrons from our metal to our non-metal. Again, creating a cation, which is positively charged, an anion, which is negatively charged. And once again, as we talked about, there's no sharing of electrons here. Again, what's holding that together is the opposite attraction between the two charges, and that is an ionic bond. You always pretty much know it's an ionic bond if you have that combination together, a metal and a non-metal. And that's different than a covalent bonding that we were talking about, which is between two non-metals. And because of their characteristics and because they're pretty much located in the same spot on the periodic table, again, as we talked about, they both really have properties where neither one wants to sort of give away their electrons. They actually both kind of want to gain electrons. So that's where we get sharing occurring. And again, as we talked about, we could have some unequal sharing, which is known as a polar covalent bond. And if you do a difference in electronegativity, like we talked about, that's like a zero. That's not a zero. That's a 0.5 to about above 2. Will give you that polar sort of bond. That also creates, if you remember, a sort of charge bond where one side of the bond is more negative, the other side is more positive due to the unequal sharing of those electrons. So the side that is more electronegative will be more negative in that side because the electrons are going to be on that side of the bond more than the other side, which will be more partially positive on that side. They also can be equal sharing of electrons. And again, if you got like a difference in electronegativity from 0 to 0.4, that is considered a non-polar covalent bond. Here with equal sharing of electrons, essentially you can think about it, it makes essentially a neutral sort of bond. So a nice equal kind of sharing of electrons. There is no kind of positive side or negative side to that bond. Sort of neutral in that sense. We finished up talking about drawing Lewis structures. And we talked about the steps that you want to do to draw Lewis structures for covalently bonded compounds or molecular type compounds. Really, you want to think about the logical arrangement of the atoms. Remember that it's usually the least electronegative atom in the center. And because of that, we will never really see hydrogen or fluorine in the center. So you don't want to do that. And for two reasons, obviously here, fluorine is the most electronegative atom you could have. So it should not be in the center. And hydrogen, as we talked about, should only have 2 electrons. So it should never be in the center. Otherwise, it will have too many electrons. So you put any of those in the center, that's an X. You don't want that. So don't do that. Probably the most important thing, right, is the total number of valence electrons. And remember that if something does have a charge, you need to adjust that. So again, if something has a positive charge, you need to subtract from your total. If something has a negative charge, that means it's gained electrons, you need to add that to your total. And once you have that arrangement, you're just going to, again, like we did, sort of put everybody on sides. And you want to, again, not triple bond or double bond out of the box, but just start with a single bond to everybody. Figure out how many electrons you use. And remember, we just kind of work on the outside in. We want to put them on as pairs of electrons. So you'll distribute the rest of those electrons as pairs of electrons until each of the outside atoms have 8, unless, of course, it's hydrogen, which should not have any dots around it. If you still have electrons at this point, as we talked about, then you would go again to the center atom and put them on as dots. If by some chance you get to that point and you are out of electrons before then you want to make sure that everybody has met the octet rule. And remember, it's really the case where if we do not meet the octet rule, what we want to do is fix it by first trying to make a double bond. And if that doesn't fix it, then we want to kind of fix it by making a triple bond. Remember that when we make a double bond or a triple bond, we essentially need to actually take a pair of electrons in to do so. And again, oxygen, we'll use that as well. And we'll go that way. And we could double bond that way. What that does is it maintains the correct number of electrons. It also will help everybody sort of complete its octet that it needs in that particular situation. And again, if a double bond doesn't fix it and you have no other options for another double bond, then you want to kind of move to a triple bond. So as we talked about, kind of the order is like single first, then if somebody is not good, try to fix it with a double, don't fix it, then try to fix it with a triple. Again, you don't want to kind of go right out of the box. We also talked about the idea, again, that you don't want to kind of do this in piecework and kind of each individual one with their valence electrons and try to figure out how they come together. That usually does not work really well for pictures. You want to think about, again, the electrons, just trying to distribute them as evenly as possible to everybody that's there in that particular molecule. Any questions on any of that stuff there? All right. So let's talk a little bit about bond length. Bond length is the distance between, obviously, two atoms within a bond. And we're going to look at some of these numbers, and you don't need to memorize these numbers for any reason. But if we look at the carbon-carbon single bond versus the carbon-carbon double bond versus carbon-carbon triple bond, what we actually see is it goes from 154 to 133 to 120. And if we look at the carbon-nitrogen single bond, double bond, and triple bond, it goes from 143 to 138 to 116. So what we're actually seeing here is every time we put a bond on, the distance between the atoms gets smaller and they get closer to each other. So if you think about it, you got like a single bond. As you put a double bond in, you got to bring those electrons to the middle. So that's going to bring everybody closer. Those positive nucleuses are going to kind of get pulled in. You make a triple bond, it's going to pull it in even further away. So every time you sort of add a bond on there, the distance between the atoms gets smaller because the negative sort of charge between the two atoms gets larger. Thank you very much. And what that ends up doing is kind of pulling the nucleuses and all the atoms kind of in closer together, so there's not as much of a distance. Now, that does have an effect on sort of the strength of the bond, and a triple bond is actually stronger than a double bond, and a double bond is actually stronger than a single bond. Double bond's not like twice as strong as a single bond or anything like that, but that is the general pattern. So I usually think about it like this, like if you grab like a brand new pencil out of the box, right, it's nice and long, you can pretty much snap it, no problem, right? If you take your pencil after you took a chemistry exam, you got like a little nubbin of a pencil left and an eraser, right? It's like that small, super hard to try to break that, right? Because everything's sort of together and very close to one another. And that's sort of the way bonds work. As we increase the number of bonds, the distance gets smaller, everybody's going to be held tighter. It's going to take a lot more energy to try to break those things. Now, we talked about sort of resonance structures as we were drawing some of those Lewis structures. And remember, resonance structures are structures that basically occur a lot of times in situations where you need to kind of make a double bond to fix a situation. And you maybe have multiple places where you could do that sort of double bond. And what that ends up doing is if there are multiple options of where you could kind of do the double bond, you could draw another Lewis structure that's an equivalent structure to the first one, and that is what's known as a resonance structure. They're usually kind of separated by these kind of two-headed arrows between the structures. So a couple ones that maybe we saw earlier, the carbonate ion. Carbonate ion does have three sort of resonance structures. Again, the double bond could be up here. We could have double bonded over there to the left, and we could have double bonded there to the right. Again, the reason this really does happen is as we sort of, and even in our Lewis structure, bring the electrons in to make that double bond, those electrons are what are referred to as being delocalized. And delocalized means that they're just kind of floating around, which means at any given moment, they may be up by this oxygen, or then they may move to sort of that oxygen, and they may move over in that way to the other oxygen. So not one individual Lewis structure may adequately sort of describe what's going on with it. So we could draw multiple kind of valid Lewis structures for the structure of something like carbonate. The true structure is probably somewhere between all three of those kind of mixed together. Again, you don't necessarily have to draw all the resin structures unless you're asked to do so. If you drew any one of those three structures, it would be perfectly fine for carbonate. But again, there are three different resin structures. Benzene is something we'll see in organic chemistry when we get there, but benzene looks like this. It is a 6-carbon ring. Everywhere here is a carbon. And it has 3 double bonds, and there's also a hydrogen at each of these carbons as well, even though usually it's not drawn in. So a lot of times you'll see the benzene ring a lot, especially when we get into organic chemistry. It looks like this with 3 double bonds. We could actually flop those double bonds into the opposite locations here. And a lot of times, because those electrons within something like benzene is delocalized, especially your book as well, they oftentimes will draw benzene with actually out the lines, and they're just kind of put like a little circle in the middle. And that circle indicates that there's kind of 3 double bonds that could kind of be moving around in those electrons. So for our book in here and our purposes, we oftentimes will see benzene kind of drawn like that, but it really is a guy that has basically 3 double bonds there. We definitely will see it more when we get into organic chemistry there a little bit later on. Now, we talked about the octet rule, and let me just be really clear for our class, everything will obey the octet rule. So if you're asked to draw any type of Lewis structure or anything like that, you should obey the octet rule, which means don't go over 8. Also, you should obey, obviously, the rule for hydrogen. It should not go over 2. But there are, in reality, exceptions to the octet rule that we will not really come across. So you just need to kind of know what the exceptions are, but you won't be asked to obviously draw any of them or anything like that. The first sort of exception to the octet rule is what is referred to as an incomplete octet. And an incomplete octet, much like the name implies, is something that's perfectly fine with less than 8. So there are certain things that are okay if they have less than 8 around them. And the big 3 on that is usually beryllium, boron, and aluminum. And most of the time, boron is the one that you see probably the most that will do that. So for example, here our BeH2, this Be only has 4 electrons around it, and it's perfectly fine with that. Boron here, which is a very common incomplete octet, is perfectly fine with just 6 electrons around it. So those are kind of the 3 that will kind of go less than 8. And it allows something like boron Bf3 there to actually act as, in certain cases, it can act as an acid in certain cases because it actually is missing some electrons and stuff like that. So there are certain things that could go less than 8. Another exception to the octet rule is what's known as an odd number of electrons. So it is possible, obviously, to get an odd number when you count up your electrons. Again, in our class, since everything will obey the octet rule, if you get an odd number for your electrons, probably you're doing something wrong for our sort of things here. Unless you come across something in a book or something like that, maybe that gives you one. But you can end up with basically an unpaired electron in that case, sometimes referred to as free radicals because they have one unpaired electron. And one unpaired electron usually makes them fairly reactive. And a lot of times in atmospheric chemistry, there's a lot of chlorine molecules that end up with one sort of electron. And what makes them really reactive is that purpose of they really kind of want to fix that situation and kind of want to get another electron and kind of complete its octet. So it makes them very, very reactive. Again, we won't have any of those to draw. The last sort of exception to the octet rule is what's known as an expanded octet. And an expanded octet, much like an incomplete octet, an expanded octet means there are some guys that are perfectly good going above 8. For example, up to 10, 12 electrons around it, and they're all good with that. Where that typically happens on the periodic table is if you look where sulfur is, and you kind of go to the right, to the left, and down from sulfur, really in the non-metal region up there on the right-hand side, they have the ability basically to go over 8. Now, the reason why they have the ability to go over 8 is if we look where sulfur is on the periodic table, it's in period number 3. And in period number 3, as we were talking about electron configuration, that is the N equals 3 level, right? And what orbitals appear on the third energy level? SP D. Yeah. So that is where d orbitals basically first start to appear, right? 3D, 4D, 5D, and so forth. So that's where those guys first start to appear. And that means everybody where sulfur is, and again, kind of below them on the periodic table, actually have those d orbitals available to them that allows them to stash all the extra electrons. So they're able to kind of go above 8 because they have those d orbitals sort of available, even if they're not using them. It gives them a place really to kind of put those electrons in. That also means, though, if you kind of go one row above them, carbon, nitrogen, oxygen, fluorine, and so forth, that is period number 2 on the periodic table, which is n is equal to 2, which means the only orbitals on the second energy level are s's and p's. They do not have d orbitals available to them. So they can never, ever go above 8 because of that. They have nowhere to put them. So those guys that are kind of below sulfur, are at sulfur and below, do have the ability to do so. So for example, SF6, if you were to draw it, I won't draw all the electrons on the outside atoms, but we'll just draw the connection here to our center atom. If we count up, this sulfur has 2, 4, 6, 8, 10, and 12 electrons around it, and it's perfectly good that way, yeah? Again, here in this class, anything that you draw should not go over 8, yes? So I caution you not to do that, yes? The reason I caution you not to do that is, well, you know, people like to look things up sometimes, and perhaps you want to draw this SO4 2 minus. And if you follow our rules here that we talked about in the way you should do it in this class, you will end up with a Lewis structure that looks something like this, which is perfectly good. Everybody has an octet. Everybody is good. Everybody's single bonded. If you have the temptation to look things up online, you will see this structure for the same thing, which clearly is an expanded octet for this compound and something you should not draw in here, yes? And because we don't draw that in here. And so you will find this structure if you look it up. So sometimes you gotta be careful, right? Make sure, you know, you don't borrow something that you shouldn't borrow in a situation like that. Why do you see the one on the right when you look online versus maybe the one on the left? Because actually in this particular case, the one on the right is actually a much better structure based on things that we don't talk about in this class. It's a much better structure than the first one. But since we don't do the expanded octet here, you shouldn't have that on your paper, yeah? So you probably should have this one on your paper. And, you know, maybe white people maybe know you looked it up if you have the other one on your paper, right? So just make sure you follow the octet rule. But really, in this case, to be truthfully honest with you, for things we don't talk about, actually, the one on the right is actually a much better structure than the one on the left. And that's something we don't talk about in this class, but there is, when you really draw Lewis structures, there are sometimes better structures than others. And there are maybe some different ways that you can put something together. And they sometimes classify as like a better structure, good structure, not so good structure, you know, and there are different ways to do it. But again, if you follow our rules, you usually will end up with a pretty good structure for a Lewis structure there. Any questions on that there? So once again, you know, you're not going to be obviously asked to draw any exceptions to the octet rule. You just need to know what they are. And again, everything that we draw in here should obey the octet rule, and don't go over that. Last thing we're going to talk about here is geometry. Our second last thing, I think, is molecular geometry. And we're going to talk about the geometry of molecules here. And the geometry of molecules are basically how they are in three-dimensional space. Based on really what we look at is how many electron pairs there are and really how many bonds. And when we do geometry, it is all about the central atom. So it's all about the one that's in the middle. That is the one that we look at. We can, again, predict it if you could draw a good Lewis structure and figure out how many electron pairs you got around your central atom, how many bonds. You can predict the three-dimensional geometry. The basis of this approach is that we basically have electrons near each other. And depending on what type of electrons we have near each other will give us some different geometries. So whether it is, for example, bonding electrons near bonding electrons, non-bonding electrons near bonding electrons, or non-bonding electrons near non-bonding electrons, depending on what combination you have going on, will affect basically the geometry and the shape of that molecule. Ultimately, the goal here is for those electrons to, frankly, get away from each other as best they can because they are both negatively charged. They really don't want to be near each other, but they cannot escape, otherwise everything would fall apart. So they're kind of locked into place. So they will keep sort of adjusting themselves until they get to an okay position for themselves that is a good distance between everybody, that will keep everybody as happy as they can be. The geometry here that we're going to talk about is VSEPR, and it stands for valence shell electron pair repulsion model. And it's really divided into two types of categories. When you draw your Lewis structure, if your center atom has no lone pairs, so basically no dots on the central atom, and if your central atom does have dots, are lone pairs, so dots on the central atom. We are going to talk about here two types of geometries. You will be responsible really for just one of them, but we're going to talk about both of them here. One is known as the electron pair geometry, and that is sometimes just referred to, I'm going to refer to that as EG, so I don't have to write it out every time. So when I write EG, it's electron pair geometry, and that describes the sort of three-dimensional arrangement of the electrons around the central atom. Then there's also the molecular geometry, sometimes referred to as the shape. And for the rest of this lecture, I'm just going to refer to that as the MG here for molecular geometry. So as we will see, in certain cases, both of these names will be the same. And in some cases, they will have some different names depending on what the situation is. Probably the most important thing to keep in mind when you're doing geometry, and only when you're doing geometry, which is everything pretty much counts as one. So if you have a single bond, if you got a double bond, or you have a triple bond, every single one of those things count as one electron pair and one bond. So it doesn't matter if it's a triple bond, doesn't matter if it's double bond, doesn't matter if it's a single bond. Everything just counts as one when you're doing geometry. Clearly, only when you're doing geometry, that is what we're looking at. The second thing there is not super important for us, but we talked about resonance structures, and you could basically apply this geometry to any resonance structure that you draw. And in most cases, it should be the same geometry, no matter which sort of picture you draw. For example, if you did for any one of those 3 pictures for carbonate, they all will come out basically with the same geometry when it's all said and done. All right, so let's take a look at this situation here. And let's just start really with the simplest situation, which is a diatomic molecule. A diatomic molecule basically means that there's only 2 things there. You have basically 2 things attached to each other. And basically, if you only have 2 things attached to each other, there is no central atom. And the only way to attach 2 things, right, is a straight line, right? So the shortest distance between 2 points is a straight line. One at one end of the straight line, one at the other end of the straight line. So it is always, for the geometry of anything that is diatomic, it is always linear. It doesn't matter if it is 2 of the same. Doesn't matter if it's 2 of the same with a double bond. Doesn't matter if it is 2 of the same with a triple bond. And not too many electrons like I just put there. Let's erase a couple. It doesn't matter if it is 2 of the same or 2 different. Everybody here is linear because there is only 2 things there, basically. So diatomic molecules are pretty much the simplest to do geometry on because it's always linear. And again, it doesn't matter the type of bond you got, single, double, triple, it's all linear. Basically just a straight point or line between the 2 atoms. Now, it does get a little bit different when we have 3 or more atoms sort of involved in terms of the geometry, and that's what we're going to talk about next. So our first example here is actually an incomplete octet. And when we kind of do geometry, there's really a couple things you want to look at. So the first thing you want to look at is always the central atom. So that should always be the only place you look at when you're doing geometry, the one that's in the middle. And there's really two things that you want to kind of figure out. You want to figure out the electron pairs that are there, the number of electron pairs, and also the number of bonds. So in this particular case, when we look at it, we have one electron pair there and one electron pair there. That is two electron pairs. Yeah. Now, when we figure out how many electron pairs are there, that will tell us the electron pair geometry. So the electron pair geometry will be, in this case, with two pairs there, it will be linear in terms of its geometry. What's going to happen in this particular case is, because there's only two electron pairs, they're going to get as far away as they can from each other. Opposite ends of a straight line basically is where they end up. That is as far away as they could get from each other. They go a little bit more than that, they're going to be too close, right? So that is as far as they can get away from each other, opposite ends of a straight line. The number of bonds in this particular case is 1 and 2 bonds. So when we have something with two electron pairs and also two bonds, the molecular geometry is also going to be linear here, about 180 degrees difference between them. Why is the name the same? The name's the same because there's only two electron pairs here. They're both bonding electrons, which means as those bonding electrons move, they have an atom attached to them. So the atom just goes with them, right? So they end up in the exact same location because the atom's attached to those electrons. So as the electrons move, so do the atoms. And again, they're able to spread themselves out basically as far as possible from one another. Questions on that there? The next type of geometry is a situation where we have one thing attached there and three others. And again, if we look at the central atom here in BF3, also an incomplete octet, the number of electron pairs in this case is 3, 1, 2, and 3 electron pairs. Again, in terms of the electron geometry name, something with 3 electron pairs is trigonal planar, or sometimes referred to as triangular. Now it also has 1, 2, and 3 bonds as well. So it also has 3 bonds. And the molecular geometry name in this case is also trigonal planar. Now, the deal on this is it is the same name because, again, the only type of electrons we have here are bonding electrons, which means they have an atom attached to them. So again, as those electrons move, the atoms move with them to the exact same location. So we end up with the exact same geometry. But the difference here, though, is in the case of BF3, we actually have an additional atom there, an additional set of electrons. So they can't get opposites of each other because these guys got to keep some distance from each other. These guys got to keep some distance from each other. And frankly, these guys cannot get too close as well. So because we now have that extra atom in there, the best they could do is this trigonal planar, which is 120 degrees. It is sometimes called triangular because, frankly, if you connect the dots here, you just made a triangle. Yeah, so it looks like a triangle basically. And again, it ends up that way with the third sort of atom that wasn't there previously. Without that third atom, they're able to get just fully across from each other. But because now we have the third one, they kind of have to go out a little bit more in each direction. So 3 electron pairs around the central atom, 3 bonds, trigonal planar for both names. Bond angle of 120 degrees. The next type of geometry is something that we see very much butchered right there in that picture. So when we redraw CH4, maybe a little bit better here. So CH4 looks like this. And again, if we go for our number of electron pairs here, 1, 2, 3, and 4. Something with 4 electron pairs The electron geometry name is tetrahedral. And in terms of bonds, it has 1, 2, 3, and 4. So number of bonds is going to be 4. The molecular geometry name is also going to be tetrahedral, or tetrahedron if you find an old book going around there. And in this situation, we end up with one extra bond in there, right? And now we have 4 atoms that kind of has to keep their distance from each other. So again, these guys has to keep their distance. They got to keep the distance. They got to keep away from each other, and they have to keep away from each other. And it ends up in this tetrahedral arrangement, which has a bond angle of 109.5, kind of almost pyramidal there on the bottom, and a triangle on each sort of face of it is basically what it kind of looks like. And again, with that 4th sort of atom there, they can't do the kind of 120. They got to, again, kind of spread out a little bit more from each other. Again, the goal here is we have electrons near electrons, so really don't want to be near each other. So they're going to kind of keep moving until they can find an acceptable sort of distance to basically stop at. Up until this point, what we have seen is both the electron pair geometry name and the molecular geometry names are the same. And the reason for that is what I've been talking about. The only type of electrons we have here are bonding electrons, right? So those bonding electrons have an atom that's with them. So as those electrons move, so do the atoms move. And basically, we end up with the exact same name for both of them. So if you ever draw your Lewis structure and you have no dots on the central atom, both the electron pair geometry name and the molecular geometry name will always be the same because you have all bonding electrons. The atoms will always end up in the same location. It is only when we start introducing non-bonding electrons that one of these names change. And when we have non-bonding electrons that sort of come into play, it is the molecular geometry name that actually starts to change. The electron pair geometry stays the same, so you still have 3 electron pairs, 4 electron pairs. But when we have non-bonding electrons, what ends up happening is a couple of things, but one thing that ends up happening is we no longer have that atom that's bonded to those electrons, right? So it gives the atom and the molecule a little bit more room to kind of spread out, and it allows those electrons to kind of spread out a little bit more because, again, that atom is not flowing with those non-bonding electrons. There's nothing attached to it. So it actually affects the molecular geometry name or the shape name because of that. And we also get a different type of interaction that starts to occur when we have non-bonding electrons. And as I mentioned before, there's really 3 types of electron interactions we could have when we have basically a Lewis structure and a bunch of bonds sort of happening. We could have bonding electrons near bonding electrons, which in your Lewis structure are lines near lines. That's like the best situation we could have in terms of electrons being near each other. Is what we were just talking about pretty much with those few examples. The next thing, which is starting to get a little bad, is non-bonding electrons near bonding electrons. So in your Lewis structure, if you got dots near lines, that's like they definitely want to kind of get a little further away from each other. And then again, they're going to be able to do so because they're not hammered down with an atom on those non-bonding electrons. So they're kind of free to move a little bit more. The atom doesn't move with them. The worst situation you can have, and where the electrons really want to get as far apart as possible, is non-bonding electrons near non-bonding electrons. So when you got some couple of pairs of dots around in your Lewis structure, that's sort of the worst situation, and that's where you're really gonna get a big difference in the geometry of the molecule, because those non-bonding electrons, now you got a couple of them that have nothing attached, so they're just gonna try to go as far away from they can. It's opposite of each other. Things that are bonded in that case also are going to try to move away from those guys because they don't want to be near them, and it's going to really affect the geometry of the molecule or the shape of the molecule. So let's take a look at a couple of examples of that. And if we draw SO2, which I think we might have did the other day, it will look something like this. And again, we still are going to take the same approach. It's all about the center atom. So we're going to look at the center atom, which is sulfur, and we're going to count our number of electron pairs. So in this case, it has 1 electron pair, 2 electron pairs, and again, remember, double bond, triple bond, single bond all counts as one electron pair there. Yes, that only counts as one. So that's a grand total of 3 electron pairs. Again, the double bonded guy counts as one, single bonded counts as one, and the 2 dots count as one. As I mentioned before, the electron geometry name does not change. So just like we saw earlier, something with 3 electron pairs is going to be trigonal planar. Now, the difference, though, is when we look at the number of bonds, we actually only have, in this case, 1 bond. And again, our double bond here counts as only 1. So we have 2 bonds in this case. So what happens in this situation is we have bonding electrons near bonding electrons, and we also now have non-bonding electrons near bonding electrons. So what happens is that sulfur with its non-bonding electrons, I'll just go this way, is going to now try to get away from those oxygens. So those oxygens are going to start to drop down away from it to try to get some distance. But they cannot go too far because they also don't want to get too close to each other as well. So as those non-bonding electrons kind of go up, the bonded guys will kind of go this way to kind of get away from each other. And what we end up with is a molecular geometry, which we'll call angular. Some people call it bent, and some people call it bent angular. I personally like to call it angular because we will see something that's called bent later on, and it actually has a different bond angle. The bond angle here is actually less than 120 degrees. So with those non-bonding electrons, because it's not attached to an atom, it can kind of go upwards. It's not going to affect the overall shape of the molecule because the ones that are bonded are going to get away, and that's what we're going to look at as the overall shape here. Questions on that one there? The next sort of example like that is NH3. If we draw NH3 here, again, looking at the center atom, the number of electron pairs, again, it doesn't matter if they're lines, doesn't matter if they're dots, you're just counting everybody around the central atom only. So 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So as we saw earlier, something with 4 electron pairs, the electron geometry name is tetrahedral. Now, when we count our bonds, we have 1, 2, and 3 bonds. And something with 4 electron pairs and 3 bonds will have a molecular geometry name or shape that's known as trigonal pyramid. And it's kind of the same idea here that's going to happen. We have these non-bonding electrons, which definitely want to be as far away from these guys as possible. But now we got those 3 bonded guys there, right? That also needs to kind of keep some distance from each other. And it makes kind of like a pyramidal shape on the bottom and a triangle from the top, hence trigonal pyramid here. And again, what's happening is, as you can see, all the bonding guys are getting near each other as best they can, and they're trying to keep as much distance from those non-bonding electrons because they don't want to really be near them, and they want to get as far away as possible. Now, this does bring up a good point about some naming. We saw earlier there our friend trigonal planar, which is 3 electron pairs and 3 bonds, and trigonal pyramid, which is 4 electron pairs and 3 bonds. There is a difference, yes, and you should state the difference when you're asked that question. You should not just write trigonal and let me choose, because I will choose an X, yes, so it'll be wrong. You should not do my other favorite answer, which is very confident with the trigonal, very confident with the P, not so confident with the rest of the writing. Like, yeah, it clearly says planar. Can't you read it? I mean, pyramid. Was it pyramid? Planar is one of those, yeah. So they are different. You cannot just write trigonal. Yeah, you got to choose trigonal planar or trigonal pyramid. Again, because they are very different. The bond angle here is related to the tetrahedral. It's less than, in this case, about 109.5. It's about 107 in this particular compound here. So it's less than 109.5. The last sort of geometry is something like in water here. And if we look at water, again, looking at the central atom, We have a number of electron pairs. 1, 2, 3, and 4. Once again, because it has 4 electron pairs, the electron geometry name there is tetrahedral. The number of bonds in this case is going to be 1 bond, 2 bonds. Now, something with 4 electron pairs and 2 bonds, is molecular geometry name is bent or V-shaped. Hence why we're going to go with angular on the previous one instead of bent. And what happens in this case is we actually have all of the worst interactions could happen. We actually have all 3 interactions of electrons happening here. We have our non-bonding electrons near our non-bonding electrons, which means they're going to try to get away as far as possible. We have our bonding electrons near bonding, and we have, for good measure, non-bonding near bonding electrons. So we have all the interactions happening. So what ends up happening is those non-bonding electrons pretty much just go sideways from each other to try to get as far away as possible. The hydrogens then kind of come down to try to get away from those guys. But again, the hydrogens can't go too close to each other because they also need to keep some distance from each other. And it ends up in this bent or V shape, which is why you typically will see water drawn like that, like an upside down V, if you will, or a bent sort of molecule like that. The reason it is different than the angular is the bond angle here is less than 109.5. The other bond angle for angular is at more like a 120-ish in that area. Something like water is like 104-ish is the actual bond angle that happens for something like water. The best way to sort of do geometry, honestly, is counting electron pairs and bonds and just knowing the geometry that goes with it. Most people cannot visualize 3-dimensional sort of orientation, myself included. So you have a table similar like this in your book. Number of electron pairs is the number of electron pairs, basically. This is our number of bonds. And again, you'll have your names that go with it. You are responsible for, let's see where it went on this tab. There it is. You are responsible for just the shape. So you're responsible for only the molecular geometry names that we talked about. You don't have to do the electron pair names for lecture, so just the molecular geometry names. Any questions on that there? All right. The last thing we're going to talk about here in this chapter is molecular polarity. So earlier on in this chapter, we talked about bond polarity. And bond polarity is where we use that difference in electronegativity. So that difference in electronegativity values is what we use for bond polarity. And bond polarity and molecular polarity are in some cases the same, and in other cases, they really are different. So the case where that is the same, come back to this and kind of do it on this page, I think. The case where both bond polarity and molecular polarity are the same is when you're dealing with diatomic molecules. And when you're dealing with diatomic molecules, for example, if we take our H2, when we look at the bond here between H2, we know that this is a nonpolar bond, right? Because if you calculated, in this particular case, the difference in electronegativity, you would get a 0 for sure because they're both the same element, right? So they both have the same electronegativity value. That means that this is a nonpolar bond in this particular case. Now, because this is a diatomic molecule, the absolutely positively only bond present is that bond. That's the entire molecule, basically. So in this case, because this is a nonpolar bond and there's only one bond in the whole thing, this would also be a nonpolar molecule. Now, if you had something like HF that we saw earlier, HF, difference in electronegativity, is something like 1.9, which makes it a polar bond, where it is more electronegative heading in that direction of the fluorine. Remember that that arrow points to the more negative side of the bond, and the back end of it, where it kind of makes a plus sign, is the more positive side. That is a polar bond in this case. And once again, for the same reasoning, that is the only bond in the entire molecule because the only bond in the molecule is polar. This would be a polar molecule as well. So probably the easiest ones to figure out, is it a polar molecule or a non-polar molecule or diatomic molecules? Because frankly, there's only one bond. So if you could correctly identify that bond as being polar or non-polar, then you know the molecule is going to be polar or non-polar because it only exists with one bond. By the way, in a polar molecule, we also draw this arrow, the same arrow we use for bond polarity. And this is what is sometimes referred to as a dipole moment. And a dipole moment is an arrow that is drawn that looks just like the one we used with electronegativity. And it points to the more negative side of the molecule and the more positive side on that side of the molecule. Only polar molecules have dipole moments. And that's because non-polar molecules equally share electrons. There is no positive side to that molecule. There is no negative side to that molecule. That molecule is essentially a neutral molecule, basically, because of the equal sharing of electrons. So if you have something that has a dipole moment, you know for sure that is a polar molecule as well. Now, if everything was that simple, that would be great, but it's chemistry, so it's not going to be, right? So when we get to 3 or more atoms, there are a couple of things that you actually have to look at to determine whether or not this molecule is going to be polar or non-polar. So when you have 3 or more atoms, you have to look at, are there polar bonds? And secondly, you have to look at the molecular geometry that we just talked about. So let's take the classic example of carbon dioxide. If we draw carbon dioxide here, which I think we did maybe at the very end last time, it will look something like this, basically a double bonded oxygen on each side. When I look at carbon dioxide, the first thing I want to figure out, does it have polar bonds? And because it contains carbon and oxygen, if I look on the periodic table, all those guys are in the same row on the periodic table. Oxygen is further to the right on the periodic table, which means it's more electronegative. So something like carbon dioxide here actually has 2 polar bonds between the carbon and the oxygen, again with the oxygen being more electronegative. So this molecule has polar bonds. So check. Now, because it has polar bonds, you may say to yourself, it would make sense that it is a polar molecule, right? Because, it's got polar bonds, so that kind of makes sense. But we do have to look at the molecular geometry here. So when we look at the molecular geometry, we're going to go to the center atom and count our electron pairs. 1 electron pair, 2 electron pairs. Again, everybody counts as 1. And in terms of bonds, 1 bond, 2 bonds. So as we just talked about, something with 2 electron pairs and 2 bonds has a molecular geometry of linear, 180 degrees apart from each other. It is basically my pencil here, or my pen I threw down here, my pen. So basically we have carbon, we have oxygen on both ends, right? So we have the oxygen on the right-hand side pulling this way, right? But we also have the oxygen on the other side pulling that way. I am actually pulling really, really hard on my pen. Is my pen going anywhere? It's not, right? So I'm pulling this way and I'm pulling back this way, right? So even though this particular compound has polar bonds, because of its geometry, they actually cancel each other out. And this is actually going to be a non-polar bond. Because not polar bonds, right? A non-polar molecule, not a bond, but a non-polar molecule in this case, because of its geometry. So what this demonstrates is you can definitely have something that has polar bonds, but because of its geometry, they actually will cancel each other out. Now, the reason that is those little lines that I drew are vectors. And I think in physics, they say that it has direction and magnitude. I fell asleep at that point, but I think in some cases, I woke back up long enough to remember that in some cases, they actually cancel each other out. In other cases, they actually add to each other. Places where they cancel each other out is when they're going in equal and opposite directions, like in my pen example, right? One going this way, one going this way. You could think of it like pulling on a rope, right? Again, pulling on the rope equally on both ends, the rope's not going to go anywhere, right? Or if they're heading in the same direction, right? You can think about like a door that swings. If there's two people on the other side pushing equally, door is not going to open, right? It's just going to be stuck there, right? And those are two ways that these things can cancel each other out. Now, if you take something like water, which we just looked at, water also has polar bonds between the hydrogen and the oxygen. Oxygen, again, going to be more electronegative. In this particular case, it does have polar bonds. And the geometry here we just did, it has 4 electron pairs and 2 bonds. That is bent or V-shaped. So in this particular case, what you have going on is you have a molecule that's kind of like this, and you got some polarity going this way, polarity going this way, kind of meeting at the top, if you want to think about it. And if you think about if this thing was on a string meeting at the top and you just pulled the string straight up, the whole thing's going to come up, right? You're going to get some movement that's going to happen. And what's going to happen here is this thing will have a net dipole moment in that direction, which is why the oxygen is more negative in water and the hydrogens are more positive in water because of the unequal sharing of electrons. And this guy will actually be a polar molecule because of its geometry. That's really why, in this case, if I remember, you add those things together, you draw one like that, they join together heading in that direction. Nobody wants to do vectors, obviously, but that's sort of what's happening in this case. So clearly, nobody wants to think about it in this way to figure out molecular polarity. There must be a shortcut. So let's talk about the shortcut, which is the much easier way of doing this. There are certain geometries which are referred to as being symmetrical. And for you guys, and again, we're talking about the molecular geometry ones that we went through. For you guys, your symmetrical geometries are trigonal planar and tetrahedral. And if you remember what each of these pretty much look like, they have no non-bonding electrons on the central atom. So if you have one of these geometries, which basically has no dots and all the outside atoms are the same, it is going to be a non-polar molecule. It's a pretty safe bet. So for example, if I have CF, and I'm not going to draw all the dots on the outside guys. If I look at this, this is what I'm looking at. I'm going to look at my central atom. I'm going to see no dots. Then I'm going to look at all the outside atoms to see that they are all the same. And then I'm going to write non-polar molecule on my paper and move on. Yes, because it will be a non-polar molecule. They are equal and opposite is what's going to happen in these cases. So each of those fluorines will end up in an equal and opposite side. And like every pulling on that rope in equal and opposite ways, they're just going to cancel each other out and it'll be a non-polar molecule. But what would happen in this situation if I swapped out one of the fluorines for a hydrogen? Will it still be non-polar in this case? The answer is it will not be, because in this case, we had equal and opposite sort of polar bonds heading that way. We still have polar bonds going in this direction, right? But the carbon-hydrogen bond is actually non-polar, yeah? So you essentially have 3 guys pulling this way and this guy actually helping a little bit, not really pulling back the other way. So now I got 3 people pulling the rope stronger than that 4th guy. The whole thing is going to move. So this will now become a polar molecule. So if you draw your Lewis structure and there's no dots on the central atom, everybody on the outside is the same, going to be non-polar molecule. If you draw your Lewis structure, no dots on the central atom, everybody on the outside is not the same, probably a safe bet to go polar. Yeah. And you're in good shape on that. What does that leave us? It leaves us really the unsymmetrical guys, which is everything that's left over pretty much. So in your case, angular, trigonal, pyramid, and bent are V-shaped. What do all these guys have in common? They got dots on the central atom. And if they have dots on the central atom, all the outside atoms are the same. It's going to be a polar molecule. Yeah. So that's really the quickest way you could do it. Pretty much dots or no dots. And is everything the same on the outside? That really leaves you only linear that you would have to worry about. And linear is pretty straightforward. It's a straight line, which means if you have a linear where they're going opposite directions, like we had a second ago, that would be nonpolar. If they're heading towards each other, that would be nonpolar. But it is possible to have something that's linear where, I should make that be. Everybody is heading in the same direction. In that case, it would be polar. So that's the only one you has to worry about. So this is how fast you could kind of do geometry. So let me just draw a bunch of different Lewis structures here, and we'll see if we can figure out molecular polarity pretty quickly here. Let's do this one here. Let's do someone we saw. Let's do this one. I think we had that one. Let's do that one. No. Let's do this one. I think we drew. Do this one for fun. Why not? That one. All right, so let's take a look. I want to throw one more here just for fun. Here, let's do. We'll do this one here. All right, so we're gonna figure out polar or non-polar molecules. This is how fast I recommend you do it. Yeah. So here's what we want to look for. Look for a pen color. All right, so I'm going to look at this guy, right? That's the central atom. Do I see dots? No. Everything on the outside is the same or different? Same. Polar or non-polar? Non-polar, right? There you go. Dots. Everything on the outside is the same or different? So polar or non-polar? Dots. Everything on the outside is the same or different? Polar or non-polar? Dots. Everything on the outside is the same? Polar or non-polar? Dots. Everything on the outside is the same? Polar or non-polar? Dots. Everything on the outside is the same? Geometry of this one? This one's actually linear. Yeah. So we have one electron pair, two electron pair. So this is the one we actually have to look at, right? Because it is that linear geometry. So this one has two electron pairs and two bonds, right? So this is linear in terms of its geometry. So we have to actually look at the bonds here and see what's going on because it's a straight line, right? Basically. Carbon hydrogen is a non-polar bond, so we don't have to worry about that. Carbon nitrogen is polar because if you look on the periodic table, nitrogen is further to the right in the same row. So we do have a polar bond going this way, and it is linear. And if I have a straight line like this, and I pull just on one end, is my pen going to go somewhere? It is, which makes it polar, yeah? So there you go. Polar or non-polar? Non-polar, right? Because that's the only bond there. Lastly here, let's do polar or non-polar, this one. It is polar, right? We have no dots, right? But everything on the outside is not the same, right? So polar. I don't think you could do molecular polarity any quicker, yes? You probably just got them all right, I hope, yes? Any questions on how to do that? That would be my recommendation on how to do it. So dots, no dots, same, not same, And you'll pretty much be good 99.99% of the time on most of them, and you'll be in good shape. Any questions on molecular polarity? Again, that is different than bond polarity, where we're just looking at the two bonds and electronegativity difference. Molecular polarity is taking everybody into account over the entire molecule, all the bonds that are present, and the geometry of its three or more atoms to see if we have overall equal sharing of electrons or non-equal. That is chapter 6, I think. Yeah, let's take a 5-minute break or so and let that all digest. Chapter 7, and chapter 7's got a lot of stuff in it. So we got equations, reactions, moles, and some important sort of calculations towards the end we'll do. So we're going to start with really equations and balancing equations. So this is a chemical equation, which obviously is the representation of a chemical reaction happening. This is a balanced equation above, and there's really two parts to an equation. The first part is what is known as the reactants, and they're always on the left-hand side of the arrow. They really are your starting material in a chemical reaction. And on the right-hand side is our products, and these are the guys that are really formed as a result of a chemical reaction taking place. And it's always reactants to products. And there are other things that sometimes show up in equations. For example, very commonly we do see the states of everything. So next to formulas, you'll sometimes see an S written, maybe an L, maybe a G, maybe an AQ. And obviously this means that thing's in the solid state, that's in the liquid state. That is in a little bit farther down, gas state. And that's the aqueous state. And that's basically a water environment. It's really a solution. Most of the reagents you use probably in lab are aqueous and solutions. It's really a homogeneous mixture is what it is. And it's two things kind of mixed together. What we do see here is a balanced equation. And whenever you have an equation or need to use an equation or give an equation, you should always make sure that it is balanced. And the way that we make sure it's balanced is we need to make sure that we have the same number of elements on each side of the arrow. They don't have to be obviously in the same things, but you should have the exact same number of things on both sides. And that is because in a chemical reaction, the only thing that happens is we pretty much take everything on the reactant side and we just break all their bonds. And that's all about electrons. And then on the product side, we just put everybody back together into new things and make bonds, which is also electrons. We never touch what's in the nucleus, so we never touch protons or neutrons. And because of that, as we know from an earlier chapter, it's the protons, right, that determines what elements we're talking about. So since protons are not touched in a chemical reaction, we never like make new elements along the way. We always have the same elements on both sides of the arrow. So when we look at this here, if you look on sort of the reactant side and the product side and just count up, what you got going on, we always look at the coefficients, which are the numbers in front. And again, if there is not a number in front of something, much like in chemistry, we oftentimes don't like to write 1 for things, but it is basically a 1 there is what that is. And we do have to multiply kind of by the subscript if there is one, and that coefficient goes for everything that's behind it, basically. So that's 2 times 2, which would tell us we have 4 hydrogens on the left-hand side. This also would be 2 times 2 there, which would tell us we have 4 hydrogens on the right-hand side. This 1, basically, 1 times 2 on the left-hand side is going to give us 2 oxygens. And again, this 2 here goes for the hydrogen that's behind it, and it also goes for the oxygen that's behind it. And once again, if there's nothing written here, again, it's assumed to be 1. So that's going to be 2 times 1, which is 2 oxygens on that side. So this is what is called a balanced equation. We basically have the exact same numbers of elements on each side, and that's always what you want. So whenever you have an equation, that's really the first thing you should really look at is to make sure that it's balanced. And if you see coefficients, in most cases, I would say it's probably going to be balanced unless somebody's trying to trick you. If you definitely don't see any numbers in front of anything, you should take a pretty hard look at it and make sure that it is either balanced or that if you need to balance it. So it's really important to do that. So let's talk about the steps to balancing equations. When we balance equations, we only play with the coefficients. So that is the only thing that we can change to balance equations. Bless you. And again, the coefficients are the numbers that come in front. So we can only change those numbers. Now, why would we not want to change the subscript here? If I change that to like a 1, what happens? That Yeah, it's no longer water, right? It changes to probably something that doesn't exist and it's not really water in the case. So we should never touch any of the little numbers, right? We should also never like insert big numbers between things, right? So it's only in front. Those are the only numbers that you can change. There's a lot of different methods. Most people do sort of a trial by error. We're going to do some here in a second. I personally try to just go with what seems the easiest to balance first, and then kind of work our way around. Um, and that's sort of the best way to do it. Kind of put some coefficients in. Eventually, things should fall into place when you're balancing the equation, and everything should be balanced. There's really just kind of two things that you do want to make sure of when it's all said and done to make sure that you have a properly balanced equation. For example, all of the coefficients need to be whole numbers. And they do need to be the simplest set of whole numbers. So what do I mean by that? Let's just say, hypothetically speaking, we balance this equation and it's balanced. But when I look at the coefficients, I have a 2, I have a 4, and I have a 6. Is it possible to reduce down all those numbers and still have whole numbers? Yeah, I could divide everybody here really by 2, and you would want to do that and get a equation that looks something like this, which is the simplest set of whole numbers. And that would be the properly balanced equation in this case. And that does sometimes happen. Sometimes people will see larger numbers to balance the equation and it will be perfectly balanced. But if you look at your coefficients and you have the ability to kind of divide by a common number and bring those coefficients down to a lower number, it still has to be a whole number. So you can't do it and get like a decimal or anything like that. Everybody there got to still hit a whole number when you do that. You need to do that to have a properly balanced equation. So let's just get into one here. So we're going to go through here and I'm going to show you sort of how I would approach this, and you could do it this way or not, but maybe you might want to do it this way. I don't know. We'll see. So I'm a big fan of, especially when you're first maybe starting to balance equations, to use sort of what I like to call like a table sort of method. And basically, we're just going to kind of keep an accounting of what we're starting with. So we have basically the reactant side, we have the product side, and we have our elements. So we have nitrogen, oxygen, and hydrogen. And just like I did on that previous one, I'm just going to go through and figure out how much of every one we have. So on the left-hand side here, we have 1 nitrogen. On the left-hand side here, we have 1 oxygen. On the left-hand side here, we have, going on the right-hand side, we have 2 hydrogens. Bottom. We have 2 hydrogens. Remember, the subscript goes to the element to the left, right, is where that goes for. So that's going to be 2 hydrogens. And we have, again, nothing written there, which means we have 1 oxygen, basically. So the nice thing about the table is a couple of things. It keeps things organized for yourself, and it also kind of gives you an idea of maybe where you want to start, right? So I could clearly see from my table, I don't even have to start with oxygen or hydrogen because they're already balanced, right? So clearly a good starting point here would be nitrogen. And remember, the only thing that we could do to balance this is to change the numbers in front. So I have 2 nitrogens on the right and only 1 on the left. So to fix that, I just need to put a big old 2 there in front on the left. Remember, when I do that, that 2 counts for everybody that's behind it. So that will count for this one, and it will count for that one as well. So now we're just going to go back from our table here. We now have 2 nitrogens, because 2 times 1. Oxygens, we now have 2. And hydrogen, we still have 2 because we really didn't do anything to it, right? Once again, looking at my table, I can see I fixed the nitrogen, but I kind of screwed up the oxygen, which is very common when you're balancing equations. you'll like fix one thing and kind of mess up something else. The good news is at the end, everything should kind of fall into place, hopefully. But again, the table does give me some direction. Clearly at this point, oxygen seems like a good place because that's the only thing that is not balanced, right? And on my table here, I can see I have 2 oxygens on the left and only 1 on the right. So I could easily fix that by going to the right-hand side and putting, again, a 2 in front of the entire formula where oxygen is, not in front of just oxygen. It's got to go in the front of the formula. And once again, this is going to count for everybody that is behind it here. And if we take our table now on the right-hand side, we still have 2 nitrogens. We now have 2 times 1 oxygen. And now we have 2 times 2 hydrogens, which is 4. So we're getting close, right? So now we can see from my table, we got pretty much the first 2 locked in. The only thing left now is hydrogen, right? We got 2 on the left and 4 on the right. We can now easily see to fix that, just go over there to the left and maybe put a 2 there. That again is going to give me 2 times 1 here for my nitrogen, 2 times 1 here for my oxygen, and 2 times 2 here, which is 4 for my hydrogen. I now have a balanced equation. Yeah. Any questions on that there? So, the table can be very helpful. They sort of point you in the right direction and keep things organized rather than just kind of randomly throwing up some numbers there on the page there on each side. All right, why don't you try one then here? All right, give it a balance and see what you come up with here. All right, let's take a look and see. Again, just going to make my table here. Reactant products here. I got carbon, hydrogen, and oxygen. So on the left-hand side to start with, I have 3 carbons. On the right-hand side, I have 1. Hydrogen on the left-hand side, I have 8. On the right-hand side, I have 2. Left-hand side oxygen, I have 2. Right-hand side oxygen, I have how many? I do have 3. I got 2 there, and not to be forgotten, right? 1 over there. So that is 3. So again, just looking at my table here, I got kind of nothing balanced. So for me, I'm just going to think about what looks easiest to balance. And for me, probably, and for maybe some of you, carbon seems like a pretty easy place to kind of start. So I got 3 carbons on the left, only 1 on the right. So I'm going to put a 3 here in front of my carbon. That again is going to count for everybody that is behind it. And that's going to give me 3 carbons. Hydrogen, I still have 2. And now for oxygen, I am up to 6 in the first one and 1 in the second one, which gets me to 7 in this case. So I've now balanced the carbon, and based on my table, I have hydrogen or oxygen where I should go next. I am going to personally go with hydrogen next. The reason I'm not going to choose oxygen is it looks a little bit difficult because on the right-hand side, oxygen's in a couple of things. And on the left-hand side, it's just by itself, right? So if I play with oxygen first, it's with a lot of other things. It's going to kind of be messed up. Hydrogen here, though, is only in one place on each side. That seems a much easier pathway. Kind of save that more complicated guy maybe for the end. So I'm going to go with the hydrogen next for that reason. I got 8 on the left. I got 2 on the right. Once again, only coefficients here, so we got to put a 4 in front of the hydrogen. That again is going to go for everybody behind it. That will give us still 3 carbons. Hydrogens now is going to be 4 times 2 right there. It's going to be 8. And now in terms of our oxygen, we still have 3 times 2 in the first one, which is 6. And now we have 4 times 1 in the second one, which is 4. 6 and 4 is 10 at this point, right? And now by saving my oxygen for the end, I can now see, not too bad to fix that. I just simply need to go to the left there and put a 5 in front of it. And now we got 3 carbons, 8 hydrogens, and 5 times 2 is 10 oxygens. Yeah. So again, if you have that sort of situation, which does occur a lot, and you got something that's a little bit easier to balance, just kind of one thing on each side, probably go for that one first, save for the guy that's got a bunch of things and a bunch of different sort of formulas for the end. Any questions on that one there? All right, let's try a couple more here. All right, let's try this one here. And by the way, if you do have things in words, you definitely want to make sure you get all the correct formulas down first and then balance it. And you always want to kind of do it that way. So if you happen to be given a problem where they don't give you the actual equation, but they just give you everything in words like nomenclature, you want to definitely start with the correct formulas and then balance. So that's really important. And kind of making our table here of everybody, boron, oxygen, and hydrogen. Left-hand side, we got 2 borons, 1 there. Oxygen on the left, we do have 3 there, and we don't want to forget about that one. So that is 4 total. On the right-hand side, this is in parentheses, so this does get distributed to everybody inside the parentheses. So we will get a 3 for our oxygen. Left-hand side, 2 hydrogens, and again, distributing that 3 into the parentheses there is going to give me 3. In this particular case, there's not a lot to work with there on the right-hand side, but it does seem like boron will still be the easiest thing to sort of balance. So I'm going to start with boron, which means I do need to put a 2 there. That's going to give me 2 borons. Now, just like normal, that coefficient goes for everybody behind it. So it goes for here, here, and here, and everybody there. That means that when we get to oxygen, we also has to multiply the 3 in and then multiply by the 2 and basically multiply. And that's going to give us a grand total of 6 oxygens. And same thing for our hydrogen. We need to multiply the 3 to our hydrogen and then also to the 2 in the front, which will give us 6. The reason for that is this is basically this, right? It is not 1, not 2, but 3 of those things, right? So 3 oxygens and 3 hydrogens basically for each unit that's there. And we got to times that by 2, which is how we get to 6 for those guys. All right, at this point, obviously, there's nothing we could do on the right-hand side, right? You definitely don't want to get in the habit of just like erasing things and putting new numbers down because it will be a long evening for you probably whenever you're doing that type of stuff. So again, we have a choice here between hydrogen and oxygen. And again, maybe you could guess which one I'm going to go for. I'm going to go for here, hydrogen, for the same reasoning. Hydrogen on the left and hydrogen on the right is just in one thing, right? On the left-hand side, I got oxygen in a couple things, right? Here and here, and one thing on that side. So again, a little bit more complicated, that oxygen. I'm going to save it for the end. So I'm going to go after the hydrogen, which I can easily turn into a 6 by putting a 3 in front of it. That's going to give me 2 for the boron. The oxygen has 3 here, and this guy goes for both. So that is 3 there and 3 there. That actually just fixed my oxygen by going after the hydrogen, right? Which sometimes happens. And obviously here, 3 times 2 in the front gives us 6, and now we are balanced. So again, kind of take that approach, maybe saving the kind of complicated stuff there for the end in this situation, especially if there are multiple things. And that is a very common thing that oftentimes happens. You kind of fix one and it'll actually fix something else along the way. That's what I mean when I said earlier, things should just kind of fall into place as you're balancing it. Eventually everything should just kind of be balanced at the end after you put a certain number of coefficients down. Any questions on that one there? All right, let's try one more here. Look, again, we're going to take kind of the same approach here, I think. So we're going to make a table here. We have reactant side, product side. We got some nitrogen, hydrogen, oxygen. Left-hand side, we have 1 nitrogen. Right-hand side, also 1 nitrogen. I got 3 hydrogens there, 2 there. 2 oxygens on the left, and we got 1 oxygen there and 1 there, which gives us 2 on the right. So looking at the table, it doesn't look too bad, and deceiving perhaps. We have everything balanced except for hydrogen. In this case, we actually have a 3 on one side and a 2 on the other side. So in this case, we actually will have to put a coefficient on both sides. And if you're not sure where you're trying to shoot for, you can just multiply those together, right? 3 times 2 is 6. So you basically want to get each of those to 6. So to get our hydrogen to 6 on the left, we need to put a 2. And to get our hydrogen to 6 on the right, we do need to put a 3 over there. So again, this is going to count for everybody behind in each case. So now if we kind of go to our table, we now have 2 nitrogens. 3 times 2 is 6 hydrogens, and we still have 2 oxygens. On the right-hand side, 1 nitrogen. Hydrogen is 3 times 2, which is 6. And oxygen here is 1 there, and we do have 3 on the back end here, which is going to give me 4. So I fixed hydrogen, but kind of screwed up everything else. So that's not so great. Perhaps once again here, I have a choice actually between hydrogen and oxygen. And for the same, not hydrogen and oxygen, choice between nitrogen and oxygen. And kind of for the same situation here, nitrogen is just going to be easier to fix, right? It's just by itself over there on the right, as opposed to oxygen that's in a couple of things on the right-hand side. So we could definitely fix the nitrogen pretty simply by putting a 2 there. And again, that's going to go for everybody behind it. That will give us a 2. We still have our 6 hydrogens from here. And now in terms of oxygen, we do have 2 from there, and we still have 3 from the back end here. That is a 5 in this case, yeah? So we have now fixed nitrogen, hydrogen, and oxygen. We clearly got coefficients on everybody. So the only thing left now is to fix the oxygen. We need to make a 2 into a 5, or we just go to the next problem. One of those two. I don't know whichever one you want to choose. Thank you for not laughing. I appreciate it. All right. So I'll just do it for myself here. It's okay. All right. So so we do need to turn this 2 into a 5. We clearly don't want to go back and start taking out coefficients and doing those type of things, unless you want to probably be there all day. So one way that we perhaps can achieve that is maybe if we use a fraction of 5 divided by 2, and that might work. Let's see. So if I take now my 2 for my nitrogen, my 6 for my hydrogen, and when I take 5/2 times 2, because this gets multiplied by each other, the 2's cancel, and I end up with a 5. So that's pretty good, right? What's bad about it, though? It's not a whole number, right? So this illustrates the point. You could definitely use a fraction to balance the equation. You sometimes do, and it's sometimes the easier way to do it in a situation like this. But you cannot leave it like this. So we do have to clear the fraction. And to clear the fraction, we have to multiply by the denominator, which in this case is a 2. We got to multiply everybody by that 2. So if we do that, that's going to give us 4NH3 plus 5O2 gives us 4NO. Again, we're just multiplying the 2 to everybody that is there. Plus 6H2O. And if I didn't screw it up here, 50-50 shot, we will still be balanced at this point. So let's see. We now have in our final equation 4 nitrogens on the left. We also have 4 on the right. We have 4 times 3 here, which is 12 hydrogens. 6 times 2 is 12. And 5 times 2 is 10. And 4 times 1 is 4. And 6 times 1 is 6. 6 and 4 is 10. And now we have a balanced equation. So how do you choose the fraction? Super simple. You choose the fraction. The top number is the number you need. So if you remember in our equation here, we needed a 5, which is why I chose 5. The bottom number should match the subscript. The subscript here is a 2, so the bottom number needs to be a 2, yeah? So top number you need, bottom number should match probably the subscript, because probably in most cases like this, you will have like a diatomic molecule like this, an element, and you'll have a subscript. So a lot of times that subscript is 2, but that's how you can always choose the right fraction. So again, if you backed up to this line here, we needed a 5, so that's why I chose 5 on top. And once again, the 2 is going to be multiplied by it there, so I need a matching number there to leave me with the top number, which is ultimately what I want. Any questions on balancing equations here? No. All right, well,